Hello guys, this is section 5.6, the fundamental theorem of algebra, or some of you guys can call the fun theorem of algebra. As it says here, as we've talked about before, the degree of the polynomial, right? So second, third, fourth, fifth power, things like that. The degree of the polynomial equation will tell you how many roots the polynomial has, right? Roots are the same thing as zeros, solutions, x-intercepts, it's all kind of the same stuff. Below are a couple different examples of graphs. We talked about this back in chapter 4, but what real solutions look like on a graph. So this first one here has two real zeros. The second one has one real zero. And the third one doesn't intersect the x-axis at all. And so it has no real zeros. Now, we'll talk about what this stuff means here in a second if there's 2, 1, or no real zeros. But like the description says, all of these are quadratic functions, meaning it's like something squared. So they should have two solutions. The solutions, however, may not always be real numbers. And that's the key thing in this section. You may have solutions that are not real. And if they're not real, that means they are complex. So remember, imaginary numbers in a plus bi form. These will sometimes be complex solutions for the polynomials. This knowledge summarizes this fundamental theorem of algebra. So down below in this box, it just reiterates that if a polynomial of degree n greater than or equal to 1 has exactly n roots, it includes multiple and complex roots. So what I mean is if we have a polynomial, say, of degree 4, you might have 4 real roots, or you might have, for example, maybe 2 real roots and 2 imaginary roots. So it can be maybe all real, or it can be a combination of real or imaginary. Let's say you have degree 5 for another example here. Well, you should expect 5 total roots. Maybe 3 of those are real, and maybe 2 are imaginary. Or maybe only one of them is real, and maybe there are 4 imaginary. Okay, so you can have a mix and match there, real and imaginary. The thing about the imaginary solutions is, though, they're always going to come in pairs. So it's always going to be an even number because when you're dealing with I, you're going to see a lot of plus or minus I. So if you have positive I as a solution, then negative I as a solution. As a complex conjugate like we talked about back in chapter 4. All right, let's go to the next page and look at an example here. This guy says, what are all the roots of x to the 5th minus x to the 4th minus 3x cubed plus 3x squared minus 4x plus 4 equals 0. So what's our degree here? Well, we are degree 5, so that means we should have 5 roots. So 1, 2, 3, 4, 5. Okay. Now to get started on this thing, I'm going to do the rational root theorem like we did last section, where I want to find the factors of my constant term, which in this case is 4, and I want to look then at my factors of my leading coefficient, which in this particular case is 1. Okay, so factors of 4, right? We've got 1, 2, and 4, right? 1 times 4 is 4, 2 times 2 is 4, and obviously plus or minus for all of these, and we'll do that here when we make our possible solutions. Then factors of 1, we're just looking at 1. So that means our possible roots, we've got plus or minus 1 over 1, plus or minus 2 over 1, and plus or minus 4 over 1. Once again, it's nice when the leading coefficient is 1. It makes all your possible roots all whole numbers, which is kind of cool. Okay, next step, we got to check and see if some of these work. So I'm going to check with positive 1. That's generally the first place we start. So I'm going to plug that in for x. We're going to get 1 to the 5th minus 1 to the 4th minus 3 times 1 cubed plus 3 times 1 squared minus 4 times 1 plus 4. So a whole bunch of 1's going on here, right? 1 to the 5th is just 1, minus 1 to the 4th, which is 1, minus 3 times 1 cubed. Well, 1 cubed is 1 times 3, so that's just 3. Plus 3 times 1 squared. Well, 1 squared is 1, so that's just 3. Minus 4 times 1, which is 4, plus 4. So we've got 1 minus 1, minus 3 plus 3, minus 4 plus 4. Anybody? What does that equal? That equals 0. So factor theorem tells us that, yes, this works. 1 is a solution. So after that now, we can start dividing, right? We know that 1 is our first root. So I'm just going to jot that in up above. Now I'm going to do my synthetic division to help me find a smaller polynomial to work with, right? So I'm going to write in all my coefficients. We got 1, negative 1, negative 3, positive 3, negative 4, positive 4. Draw the line. And let's go ahead and start this process. I'm going to bring the 1 down up front. 1 down low. 1 times 1 is 1. Negative 1 plus 1 is 0. 0 times 1 is 0. Negative 3 plus 0 is negative 3. Negative 3 times 1 is negative 3. 3 minus 3 is 0. 0 times 1, 0. Negative 4 plus 0, negative 4. Negative 4 times 1 is negative 4. And 4 minus 4 is 0. So our remainder is 0. Great. We're left with a whole bunch of numbers here, though. 1, 0, negative 3, 0, and negative 4. And remember, these are coefficients of our answer. Now, if we started with degree 5, this one here is going to start with degree 4, and then go down to x to the third, x squared, x, and then our constant term is that negative 4. So this answer should be x to the 4th plus 0x cubed. I'm just going to leave that out since it's 0. Minus 3x squared plus 0x. Again, I'm going to leave that out. And then minus 4. So here's our smaller polynomial now. And if you notice, that itself is degree 4, which is going to contain our remaining 4 roots, which should make sense. Now, if you notice this is a situation similar to something we did last week. So off to the side here, I'm going to remind us about how I compared these types of problems to simpler quadratics, right? That simpler quadratic, that x squared minus 3x minus 4, that's going to factor down relatively easily. You guys can look at that and you can probably figure out pretty quickly that this is x minus 4 times x plus 1. So we're going to take that same approach here, except instead of it just being x and x, it's going to be x squared minus 4 and x squared plus 1. Okay. Does everybody still see that? Now, if you remember last week when we did this, you'll notice that we have some difference of squares in here, right? X squared minus 4, well heck, that thing factors down how? It should be x plus 2 and x minus 2. And then the other half of that, the x squared plus 1, that thing can break down also. But this is a little different than what we've seen so far. So again, off to the side here, I'm dealing with x squared plus 1. And the whole idea is we're going to figure out what value of x is going to make this thing equal to 0. So if I go through the steps in solving here, x squared equals negative 1. And then I take the square root of that, which is plus or minus square root of negative 1. I get something like this. Now, hopefully you remember what the square root of negative 1 is. Anybody? That's going to be plus or minus I. So there's that imaginary number I talked about earlier, right? Square root of negative 1 is I. So that means my two answers from the x squared plus 1, they break down into x plus I and x minus I. So here are my final 4 solutions, guys. You see that? We have negative 2, positive 2, negative I, and positive I. And I'm going to fill those in up top. So 1, negative 2, 2, negative I, positive I, those are my 5 roots for this example. Okay. Good. Hopefully we're doing okay. The last one here. Not quite as elaborate because it's only x to the 4th. So this one then is degree 4, which means we should have 4 roots. Okay. Cool. Take a look at the polynomial here. What's the first thing we notice? Well, it's x to the 4th. And you might try and do your rational root theorem and take factors of the constant over factors of the leading coefficient. Leading coefficient's obviously 1, but if you look at the tail end, there is no constant. Where the heck is it? Well, the reason there's no constant is because there's an x in every term. So when there's an x in every term, let's pull that out. That's a greatest common factor. So we have x cubed plus 2x squared minus 13x plus 10. Now we have a constant here, okay? And this quartic function that was degree 4 is now a cubic function, degree 3. So let's look focusing in on this x cubed plus 2x squared minus 13x plus 10. We want to do rational root theorem, so I need factors of 10, and I'm going to compare that to factors of my leading coefficient, which is 1. Right? So factors of 10, 1, 2, 5, and 10. Factors of 1, just 1. So it means my possible roots are going to look like plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 5 over 1, and plus or minus 10 over 1. Okay, so we got to go ahead and check those out. Let's check 1. When I plug in 1 to this function, I'm going to get 1 to the 3rd plus 2 times 1 squared minus 13 times 1 plus 10. 1 cubed is 1. 2 times 1 squared is 2. Minus 13 times 1 is minus 13. And then we have a plus 10. So 1 plus 2, that's 3. 3 minus 13 is negative 10. Negative 10 plus 10 equals 0. So we have a winner here. 1 is one of our roots. So I'm going to jot that in up top. Now I'm going to go ahead and divide, right? Use our synthetic division. I'm going to plug in my coefficients, which I had 1, 2, negative 13, and 10. Okay, so synthetic division sets up for us here. I'm going to go ahead and start this process. Bring down the 1. 1 times 1 is 1. 2 plus 1 is 3. 3 times 1 is 3. Negative 13 plus 3 is negative 10. Negative 10 times 1 is negative 10. And 10 minus 10 is 0. So good for us. We have a remainder of 0. 1, 3, and negative 10 are our coefficients. So that's going to produce x squared plus 3x minus 10. And that has 2 of our factors in here, right? That'll be 2 of our roots. Can we factor this thing down? I think so. You should hopefully look at that and see that it becomes x plus 5 and x minus 2. So that means the solutions from here are negative 5 and positive 2. So 1, negative 5, 2. Uh-oh, we're missing a root. What are we missing? Where is that 4th root coming from? It comes from that GCF we pulled out in the very beginning. Whenever you have an x in front, that matches up with what? Yeah, 0. So 0 is also a root in this problem. So our 4 roots, 1, negative 5, 2, and 0. Good job on that. If you have questions, watch this again. Feel free to go back and pause, rewind. This again is on my YouTube channel. Your homework is on the calendar. It is page 322, numbers 8 through 15, okay? So go ahead and get working on that.